Okay guys, this is your last review for physics, PAP physics. I'm going to try to list the number that I'm doing at the front of each one so that you can just kind of scroll through and see the number. So like for instance, I'll just write 1, and then if you need like number 1, you can scroll through and find it. Alright, so number 1, we are going to do an electrical potential of 1 joule per coulomb is equal to, that is 1 volt. So a joule per coulomb is equal to 1 volt. Alright? Also just electrical potential in general, if you see that, that is voltage. Alright? So next we have number 2. And on number 2, we are going to be working with this formula. Electric field is equal to the electric force divided by charge. And this says the electric field is 2 times 10 to the 5th newtons per coulomb, and our electric force is that. Now, Q is kind of an unknown quantity, but it's a proton, and a proton has a fundamental charge of 1.6 times 10 to the negative 19th coulombs. So that is the charge. Since it's a protein going, or not a protein, sorry, a proton going through this electric field, it experiences a force based upon its charge, which is 1.6 times 10 to the negative 19th. And if you multiply these two things together, you should get 3.2 times 10 to the negative 14th, or C. Alright, next up we got 3. 3 is which could not be accelerated using an electric field. The answer is a photon, and the reason a photon couldn't be accelerated using an electric field is it is electrically neutral. The other 3, an electron has a negative charge, a positron has a positive charge, and an alpha particle has 2 protons and 2 neutrons, so it's got a +2 charge. Alright, so electron, -1, positron, +1, alpha particle +2, and so they cannot be accelerated in, or these can be accelerated in an electric field. The photon cannot. All right, number 4. Field lines. If it's a positive object, field lines always are drawn out from the positive object into a negative object, and if we're looking at A, you just draw a field line. There's point A. You just draw a field line to it in that direction. So the answer turns out to be A. Number 5. Okay, number 5. 2 charges that are 2 meters apart repel each other with a force of 2 times 10 to the negative 5th newtons. If the distance between the charges is 1 meter, the force of repulsion will be. Alright, so we start off with 2 meters, and at 2 meters we have a force of 2 times 10 to the negative 5 newtons. We are at 1 meter, and we want to know the force now. Well, there's an easy way to do this, and the easy way to do this is to say, okay, how do these two relate to each other? Well, 1 meter is clearly half of 2 meters, so we can plug it into the 1 times 1 times 1 divided by 1/2 squared, and we can see that we get 4 times the force if we half the distance. So if we half the distance, we get 4 times the force. 4 times the force would be 8 times 10 to the negative 5th newtons. The end. Alright, number 6. Number 6. As shown in the diagram, a neutral pith ball suspended on string is attached to a positively charged rod. During contact with the rod, the pith ball, well, you can't transfer protons, so no protons can be transferred, so we know C and D are out. So the question becomes, does it gain or does it lose electrons? Well, if the pith ball is negative, if the pith ball is attracted, let's just say it's neutral, alright, but it's right here by the positive object, then this positive object will suck electrons off. A positive object wants electrons, and a negative object wants to get rid of them. So number 6, the answer is the pith ball should lose electrons. Alright, pith ball should lose electrons. Alright, number 7. Which diagram best represents the electric field of the point charge? The correct answer is A, because it's a positive particle with the field lines going out from the particle. Alright, so this is number 10. Okay, so number 8. Alright, number 8. A circuit has a current of 5 amps flowing through it. How long does it take 30 coulombs of charge to be transferred? Well, on this one, we've got to do this formula. I is equal to Q divided by T. This is current is equal to current is equal to charge divided by time. And so we plug in 5 equals 30 because coulombs is a measurement of charge divided by time. Solve for T, we get 6 seconds equals T. All right, next up, number 9. Number 9 says, shown are copper wires with identical cross-sections which have the least resistance. All right, so on this one, please remember the following things affect it: temp, length, area. All right, higher temp makes the resistance go up, and obviously the reverse is true, or the reverse is also true. At lower temp makes it go down. Length, longer, resistance goes up. Shorter, obviously resistance goes down. Area, bigger, resistance goes down. Smaller, resistance goes up. All right, so on number 9, we're trying to figure out the least resistance. Since higher temperatures make the resistance go up, we know it's not the things at 80 degrees Celsius. And then since the longer one has the higher resistance, we know it's got to be B, 1 meter at 20 degrees. All right, number 10. The circuit contains a power supply and 2 resistors as shown. What is the voltage across resistor R? Well, on a series circuit, the voltage drop across each resistor has to be added up to be the total voltage. So voltage total should equal the voltage drop over 1 plus the voltage drop over 2 and so on. In this case, we know that the total is 12 volts. We know that the first one dropped 4 volts and the second one then had to drop some amount that was equal to that. So that means that it had to drop 8 volts to equal 12. 4 plus 8 is 12. All right, number 11. If the resistance of a circuit is doubled and the voltage remains unchanged, the current flowing in the circuit will be 1/2 as much. Now, why is that? Well, V is equal to IR. All right, so we're looking for the relationship for current. So we're just going to solve for current. V divided by R is equal to the current. So the resistance of the circuit is doubled and the voltage stays unchanged. So voltage stays the same, but I put a 2 there. Right now, if the original current was V divided by R, the new current is equal to 1/2 V divided by R. All right, so it would be cut in half. All right, number 12. Electrical impulses are used to resist the flow of, the answer is electrons. Electrical insulators resist the flow of electrons. I'm not going to do this one. This one's not going to be dignified with taking up space. Number 13. Number 13, the resistance of a wire is determined by the voltmeter and meter method. The voltmeter reads 10 volts and the resistance is 5 ohms. Find the energy that the resistor used by the resistor in 40 seconds. So these are the things you need to know. Power equals, whoops, that's supposed to be power. Power equals voltage times current, and power is equal to energy divided by time. So we need this first one to figure out the current. So voltage is equal to 10 and resistance is equal to 5, so the current is equal to 2 amps. So now we can find the power. The power is equal to 10 times 2, which is equal to 20 watts. And then now we can go down here and say 20 watts is equal to the energy divided by 40 seconds, and that gives us energy of 800 joules. All right, number 14. 14 is just this right here. Voltage total equals voltage 1 plus voltage 2 if they're in series. So voltage total is equal to 5 plus 10, which is equal to 15. Okay, 15 volts, which would be C. 15. As the temperature of copper wire is decreased, its electrical resistance is decreased as well. This was our temperature relationship. If temperature goes up, resistance goes up. If temperature goes down, resistance goes down. All right, so 16. 16 says, which graph shown indicates the relationship between resistance of a wire and its length? Well, the resistance goes up as it gets longer, so the answer is B. Resistance length, it goes up like that. So number 16 should be B. 17. If a cross-sectional area of wire, if a cross-section area equal to A has a resistance of R, then another wire of the same material with a cross-section equal to 2A will have a resistance of R divided by 2. There's a direct relationship between area and resistance. So if the resistance is inversely related to area, so something like this. So these shouldn't be equal signs; they should be related to signs. All right, so it's inversely related. So if I double the area, the resistance is related to 1/2 A. All right, so that's number 17. All right, number 18. 18. At room temperature, which segment of copper wire has the highest resistance? Well, let's look at it. First of all, we know that highest resistance is going to be the longer ones. So we're looking at the 2-meter sections. And then the second thing we know is that it's going to be the smaller areas, so it's got to be B. All right? Since they're the same temperature, it's the longer length and the smaller area that wins. All right, number 19. If the potential difference across the 12-ohm resistor is 4 volts, then the current through the resistor is, so we go V is equal to IR. We got 4 volts, we've got 12 ohms, and we're looking for I, so it should be 1/3 of an amp. A. Number 20. The ratio of the potential difference across a conductor to the current in the conductor is called the... Alright, so it's the ratio of potential difference. Potential difference is voltage, remember. And we're trying to figure out the relationship between the voltage and the current. So that ratio, voltage divided by current, is the resistance. Alright, because V is equal to IR, so V divided by I is equal to R. That's number 20. Number 20. Alright, number 21. Which graph represents a circuit at constant temperature that obeys Ohm's law? Well, if it's at constant temperature, remember that voltage is equal to current times resistance. So if the resistor stays the same, which it will if it's at constant temperature, and I raise I, what has to happen to V? It also gets raised. So as I goes up, V should go up, and vice versa. So it should look like this. Alright, which would be D. Number 10, or sorry, not 10, 22. Number 22, an electric iron draws a current of 5 amps and has a resistance of 20 ohms. The amount of energy used by the iron in 40 seconds is. So this is just like 13. We're doing voltage equals current times resistance. Power is equal to voltage times current. Power is equal to energy divided by time. So the first one we were trying to figure out the voltage. So voltage should be equal to 5 times 20, or 100. So it should be 100 volts. 100 volts times 5 amps is equal to 500. And then that's 500 watts. 500 watts equals the energy divided by 40 seconds. And so we should get 20,000 joules. Alright, next up we have 23. So number 23, what is the approximate amount of electrical energy needed to operate a 1600 watt toaster for 60 seconds? Power is equal to energy divided by time. So we get 1600 equals energy divided by 60. And if you get 60 times 1600, you get 96,000 joules. Number 24, another one looking at the smallest resistance, though. They're all at the same temperature, so smallest resistance is the shortest and the smallest area. Or sorry, shortest and the largest area. So it should be C, shortest, largest area. Remember, shorter they are, less resistance. Bigger they are, less resistance. Colder they are, less resistance. Compared to the total resistance, so 24 doesn't get a drawing. 25, compared to the total resistance of 2 5-ohm resistors connected in series, the total resistance of 2 5-ohm resistors connected in parallel is, well, the resistance total in series is just equal to 5 plus 5, which would be 10. But in parallel, it's 1 over R total, so it would be 1/5 plus 1/5, which would be 2/5, and then you have to invert it, so it would be 2.5 ohms. And so clearly, if they're in series, they have a bigger resistance. Number 26. Nearly done here. Alright, so 26. The diagram here shows a resistor of 5 ohms and a resistor of 10 ohms connected in parallel in a circuit. What is the total resistance of the circuit? So we do 1/5 plus 1/10 equals 1 over R total. And so we would do 0.2 plus 0.1 equals 1 over R total. This is 0.3, which would be 3/10. And then we have to invert that, so you get 10 divided by 3 equals R total. And if you can do simple math, that would be 3.333, which would be less than 5 ohms, which is letter A. 27. Alright, so we're supposed to base our answer based upon this diagram here. The voltage drop across R1 is, well, voltage drop is equal to V is equal to IR. So the voltage is equal to the current, which is 8 amps in this case, times the resistor, which is 1, so the voltage should be 8. That should be the voltage drop. What is the total resistance of this circuit? Well, it's series, so you just add them up. 1 plus 2 is 3. So 28 should be 1 plus 2 equals 3. So it should be C. 29. In the circuit diagram shown, which is the correct reading for the second voltmeter? Alright, so we know there's 110 volts total. We know that we've used 20 volts and we've used another 20 volts. So that leaves us with 70 volts, and that's the answer, 70 volts. Alright, number 30. 5 ohm and 10 ohm resistor are connected in series. The current in the 5 ohm resistor is 2 amperes. The current in the 10 ohm resistor is also 2 amperes because they all get the same current. 31. Last one. Looks like this. This is the drawing you should get. You should have 2 resistors, one 20 ohms, one 5 ohms. The voltage is 24 amps, and, whoops, I don't know what that N was. 24 amps, or volts rather, and it's got an ammeter right here. So that's where the ammeter is. Alright, now, we're supposed to find the current, so we do 1/5 plus 1/20 equals 1 over R total. That gives us 0.25, or 1/4 equals 1 over R total, and that gives us R total is equal to 4 ohms. Now, voltage, if you'll remember, is equal to IR. So we have 24 volts, current's unknown, and resistor is 4. The resistance is 4, so 4 divided by 24 is 6 amps. And that would be your answer, 31. Alright, I wish you all the best of luck on this test. I think you should do well. Alright, so happy studying. Good luck.